Hi. I'm going to talk about my final project on handwritten text recognition using EMNIST dataset. Uh, the problem statement for me was uh, we had a lot of success in using the standard EMNIST dataset on which was built up on top of digits. Uh, uh, but there is another extended version of it called EMNIST, uh, but that hasn't gained that much traction, and it was losing out on peak accuracy, as you can see here. So in my attempt here in this project is to see if there is a way I can make some analysis and try coming up with a network which can use this EMNIST dataset and make better predictions. So a little background on this: EMNIST is extension of the MNIST dataset. It's the same image structure as far as the data, individual image data is concerned. And here is a basic example of how the images are actually transformed in this dataset. It's pretty standard stuff. The software and technology side, I didn't go outside of the basic libraries that we've used in our course so far. So nothing fancy here. Next is the EMNIST dataset. If you want to know more about this, you can always visit this NIST website. But this research paper does a pretty good job of explaining what the dataset is and what the different categories are, what the different analysis was made under this. So it's pretty good read. But for my interest in this project, I picked one of the one from the six different kinds of data that this MNIST dataset provided, and it was the bi-class dataset. As you can see, it's 62 classes. It has got pretty good, decent size as far as training and testing set is concerned, and the final number is pretty impressive as well. So we are hoping that this would be pretty good for our models that we will look at later on. There are total 62 classes. It comprises 0 to 9, A to Z, and capital A to Z. And I'm using in particularly the MATLAB dataset, which is around 263 MB. So the overview of steps is pretty standard. We start off with preparing the data set. So we download, we pre-process, we split. I'll talk more about this in a bit. Then we define models and then train on the models. And then we update the models and repeat the steps. And in each of these models, in the process of training, we note the final accuracy and analyze the which model worked best. And then we test, make predictions on the model, which is what a demo will be consisting of. In the process of to pre-process the data set, first we need to download it, and this is the name of the file you should see once you download it from this link I have provided. Pretty standard stuff of loading the data set. We confirm the data structure here. So data set is the key, which is very important and contains all the train, test, and mapping split for us. For a further analysis, we tried printing one of the images directly from the dataset, and you can see it looks pretty obscure, very hard to read, as if the images are flipped or rotated. So I had to build a custom function which reverses the process and help you get the correct image, which is the critical piece in our pre-processing step. As now you can see, after the pre-processing of rotation and flipping, you can see you can read it pretty easily. It's letter 4 and digit 4 and letter N. We further had to pre-process the individual images into float 32 types, normalized it, pretty basic stuff which we had to do in order to help out with numerical computation later on. Another important thing we had to do was save the mapping file. The mapping file will be important when it is time to make predictions. So this was the basic high-level overview of the steps included in pre-processing. If you want to see the exact steps that were taken, you navigate to the project folder, and in that folder you look for this data pre-processing.python file, and in this it contains everything that we have discussed so far, and final we return all the training images, test labels, testing images, and testing labels, which is what we'll use from our Python files. for training. Next, we move on to the models. We build a very basic, start off with a very basic model. I say basic because it has got only two count 2D layer, corresponding max pooling layer flattened, and two dense, and the outermost dense layer has 62 as total number of classes, and we use 88 delta as the optimizer. Uh, let's look at the notebook, actually, which has this. If I open the notebook called Model Simple, I can see it has all the imports. It got the standard initialization of where the data file is. It needs to be in this data set folder. Uh, and then we define the batch size, the epochs, and then the logic to get the data, and then the split, and finally the model which we went through, and then the fit. Um, and then the process of training. Um, as you can see here, around 15th or 16th epoch, you can see the network is doing pretty good job at prediction, at accuracy. Suddenly dropped to 0.05, and so does the validation accuracy. And this trend kind of kept on till the 25th epoch. So clearly there was a problem with the model, and hence I decided to change the optimizer in the process. And this time I changed it to RMS prop. So I named it simple model with RMS optimizer model. The learning rate was 10 to the power minus 4. Keeping everything else same, I just started training process again, and this time my model actually finished with an accuracy of 87 training accuracy, and around 86 validation accuracy, which is pretty good for the first attempt. So excuse me. All the epochs this time, as you see, ran without any issues. So we are pretty good with this, the results here. So next one, we moved on to define a model which contains the image augmentation, which use the Keras image data generator API, applied some rotation range, zoom, and shear effect uh, to our data pre-processing method. Um, and that contains that in the process increased our training, because we applied this augmentation to our training data, and this helped to increase the range of our data in the hope that this will increase accuracy. So once we ran the model, we found that the performance didn't really improve. Actually, the training accuracy reduced a little bit, and you can see there is a little bit of overfitting, the around for the validation accuracy, but still, it was close to 85-ish, which is not super bad, but not better than what we found with our simple RMS prop optimizer. So augmentation was clearly not a good idea. If you want to see more on how the augmentation was done, I have uploaded this folder that ends with image aug, and if you navigate to the data pre-processing folder Python file, there I have shown how the augmentation is made, and how the augmentation is added on top of the training images. Uh, Next, the final model which I took a stab at was the deep model. I say it is deep because I have almost doubled the number of layers here, in the hope that it increases the performance. I kept everything same, everything else the same, the parameters, the data file, the split, everything else remained the same. Um, uh, and if you see the final accuracy and validation accuracy was still, not didn't get better than what we found with RMS. It got close to 85, but then dipped down a little bit towards the end. But the training accuracy was always below validation accuracy, and there is a little bit of overfitting as well. So clearly, this deeper model didn't help us either. So before we conclude with what we have done with all these different models so far, let's move on to a quick demonstration. Um, so to do the demo, you can either start with the training process if you want to see all the models on your own. So to do that, you unzip the folder here, the zip file I've uploaded. You just unzip it and make sure you have the dataset folder with the EMNIST 5 class dataset downloaded from the web. And then make sure that you have the model RMS model simple with RMS proper IPYNB file there in the folder, as well as the data pre-processing. Once everything is ready, you just go ahead and run the notebook, and that should generate the model for you and the mapping file for you, which will be needed for making predictions later on in the demo. So I hope you can just run it as is file before you can run this notebook which does the training for you. Let's move on to the fun part, which is to make the prediction. To make the prediction, all you need to do is locate the run.py file, which is under the same folder, this run.py file, and just on the command prompt, all you need to do is once you run it, it will wait for on a prompt saying that it's ready for this URL, and all you need to do is switch over to the URL. Let me quickly show it to you. So I've opened this. I have my model running. Uh, once this is up and running, this provides you an interface where you can enter a character. Like say I enter it with using a mouse A, and I asked it to make a prediction. As you can see, it makes a prediction. Let me ask it to make a prediction on a digit. Okay, as you can see, it makes a good prediction. Let me see if it can make a prediction on a small letter next. Okay, it got confused. So as you can see, it does a pretty good or a decent job of predicting, your what a user would have typed, and you can clearly see, I've used a web interface. Of course, I kind of borrowed this idea from net. I provided the links to where I borrowed this interface from, but this idea could be easily extended onto any touch enabled device where the user could use their fingers to type in, and as long as you have a model which is trained to recognize the characters, it could do a pretty good job. I know this is only on a single digit or single character, but there could be other efficient ways for which you can increase this to say 2 digits or 2 characters. There's so much more we can do on this. Uh, uh, since we have seen the demo and you can see we have seen it functional, let's move on to the concluding analysis, which is very important, I feel. So we looked at all these different models, and we reached a high accuracy of 85 or 87, which is still better than what the original paper had, original researchers had, achieved. Um, but even with so many variations of our models, we still couldn't, make any better predictions. So in the process to figure out why that happened, uh, I decided to draw the confusion matrix. The confusion matrix was actually a huge file because there is a 62 class. So the confusion matrix was pretty big. So I borrowed again a logic which helps us print this. I just saved it to a file, and this is confusion matrix.jpg. It contains all the values in the x level. It has the true levels. Y-axis has the true level, and x-axis has the predictor level. So if you see on the diagonals is where you entered F and it made a prediction F. So it looks pretty good here, but there are clearly areas uh, which it didn't make a good prediction, like F was entered and it saw it as E, sorry, capital F, and it saw it as small f. So there is a trend as to capital letters being confused by small letters, and it seems pretty natural. And there is another kind of confusion, like capital L being confused as 1, O being confused with 0, Q being confused with 9. All of this seems pretty natural to me. Nothing that a network could be easily confused with. So, so this was the final conclusion.